Everybody, welcome to the webinar. This is the second part of today's session in the afternoon at 3 o'clock in Taiwan and morning. I think also afternoon, but early afternoon, I suppose, in Finland, Helsinki. And we are very happy to have Professor Esa Kallio from Aalto University to give a talk on the cubesat program, in his lab in his university. And Professor Kallio is himself is an expert on MHD, I would say, plasma simulation. And he already gave a talk at the other moon seminar of our program. So if you're interested, and to know what other things Professor Kallio is doing, please go to that. See that video. And now, Esa, are you ready? Yes, please.
Thank you. Thank you, first of all, for the possibility to give a presentation in your seminar. And so, yes, my name is Esa Kallio, and I'm going to tell about our Suomi cubesat project. Briefly about the background, why we made it, and also how we made it, what are the goals. Actually, we have quite many goals. And actually, what we are now doing and what we have done during the last 2 years that we have been into space, and something about preliminary results and something what we have learned during this project. So first, background research goals, 2 years. Then I will actually tell about our two already now. Maybe I mentioned that we have two payloads, research payloads. One is the camera, and the second is the radio wave instrument, radio spectrometer. And I will introduce those instruments, something I will show a little bit about the data, and also I will mention what kind of tools we have developed to analyze the data, and then briefly about some lessons to learn, what we have learned. So maybe about first briefly about the project. This project is Suomi cubesat project is a joint project between Aalto University and the Finnish Meteorological Institute. So at Aalto University, of course, because it's a university, and so many students involved in this project. And Finnish Meteorological Institute, their main role was on board software, and they are also contributing to the data analysis and to really make science by using the instrument data. And it was supported by many other universities, government organizations, and companies. We have, well, maybe I will start by saying the Suomi cubesat name comes, the background is that the Suomi, actually, it is Finland in Finnish language. And the SATA, it doesn't mean that we have 100 cube satellites. We only have one small 1-unit cube satellite. But SATA means that it is a jubilee satellite to celebrate 100-year Finland. So we had 100th independence in 2017 in December. And maybe that also tells about, I'm actually going to tell about research goals, science goals. But because it was also celebrate the Finnish country, so it had a wider goal. And one goal is to really to inspire, especially young people, to be involved in science, mathematics, physics, space, and in techniques. And so we had quite many outreach activities during, and still have outreach activities in our project. And actually that is the reason why most actually our web pages, actually you can see a screen capture on the right hand side, why they have written in Finnish. And I apologize that we only have one English page. So if you go to this English part, so but anyway, it gives some background information about our project and about our many goals that we have. So Suomi cubesat, it's the third satellite built and designed at Aalto University after Aalto 1, Aalto 2 satellite. And as those pictures or photographs a little bit shows, so one goal at the university level is, of course, that the students can learn how to make space devices, how to really use technology that can be used in space. And for example, we have the vibration facilities in 100 kilometers from our department. There is you can see one picture about that one. In the middle, you can see our electronic laboratory in our space laboratory. And at the bottom, a small picture about our clean room. And actually here you can see students who involved in Suomi Sata. And you can see actually this Suomi Sata space instrument, spacecraft at the bottom. It was launched on December 2018 in California in a Falcon 9. And okay, maybe you might know that there are more and more trends to use recycle also in space devices. And actually this first stage B1046, it was reused several times until actually a year ago it didn't return back in one piece because it was used in this kind of crew dragon in flight abort test. So that was in purpose destroyed. The orbit is the polar orbit because we really want to measure auroras. We want to make ionosphere research, and especially around Finland and in Scandinavia. So here actually you can see the trajectory, the ground track during one day. And you can see that part of those are on the day side and part of the night side. And it also affects how we operate our instruments. So here you can see a photograph of Suomi Sata. And actually I also have a one-to-one copy of these satellites. And it's a one unit. So one unit means that it's 10 centimeters, 10 meters, 10 centimeters size in 1 liter in volume, mass about 1.3 kilograms. Here in this slide, there is 5 solar panel faces, those black, and then there is one, this kind of white, what you can see at the top. So at the top, there is a hole, and because there is a camera objective. And the second instrument is the radio wave instrument, and it requires antennas. And those 2 antennas are encapsulated inside 2 plastic peak material plastic planes. And you can actually see those 2 antennas, a little bit like a dark regions at the top. And of course, there are, for communication reasons, other antennas. Yes, platform, yes, solar panels, I have mentioned communication antennas. The research goal is that to make space weather research, but especially ionosphere research. So to really investigate how the sun affects to the planet Earth, its near space, so-called geospace, by the solar wind and by the photons, by the sunlight, especially EUV and X-rays. And there are many these kind of devices on ground in Scandinavia, in Finland, or northern of Finland, to really make a space weather research. Let's say here you can see the ice cut, one of ice cut antennas. I want to maybe demonstrate what we want to use by using our virtual reality. Maybe I don't know, is it this maybe you can now see better. We have made a virtual reality that includes our space weather simulation results. And in this animation, actually, you can see our simulation. I will come back to those simulations later that we use to analyze radio spectrometer data. That in the simulation, we have launched radio waves from Helsinki. And you can see actually how those radio waves are going upward. They are propagating, but they are not propagating at like a straight line because ionosphere is affecting the propagation of radio waves. And some of those waves are bouncing back, some of those are refracting, reflecting, as you can see in this animation. So maybe I started, I don't, hopefully you can see it. So here you can see some radio waves actually going through the ionosphere. And what we want to do in our radio spectrometer, that when we fly over those kind of radio wave sources, we try to measure those radio waves and in such a way get information about the ionosphere. And then we have a camera, and in camera our main research goal is to take a picture of auroras. And in general, as I mentioned, the goal with the camera and radio spectrometer is to understand near Earth space and to take space weather research. What is happening around Earth in the magnetosphere? And actually here you can see also the moon, but that's nice picture. And actually, if you are interested, you can see at the bottom of the web page that you can download our virtual reality software. You can actually fly around Mercury, Venus, Comet, Menga, and also get around Earth and get the view of what the Suomi Sata will observe. So observation, so how we really do it? We have two instruments. We have a day and night. Sometimes we are on days on sunlight, somehow we are on the night side. So in the first phase, we start to use camera as much as possible. And we started by making the most easy photographing, take a day side photographs. Because it's easy to see by naked eye how the camera works when you look those kind of photographs. I saw a couple of examples about our photographs a little bit later. But our main goal is to use that camera on the night side. I saw also an example of night side photographs, especially take a photograph of auroras. But we also do see sometimes the moon and stars. I will show that examples later. But our main research instrument was this radio spectrometer. And after this first phase, we started the second phase. And actually, this is the phase where we are at the moment. And I believe that this is the phase where we will be several years. So we will focus on radio wave spectrometer observations. And maybe already now, always it takes a little bit or quite a lot of time to really become familiar with the instrument. For example, we have a different onboard programmed data modes how to use the instrument. We can use as a constant frequency. At the maximum, we can get 1,000 measurements per second. And actually, we use that for local measurement. So maybe 10 minutes, 15 minutes measurements. But then we have also a little bit lower resolution, 5 data points per second, average values. And then we can make a global measurements. We can make a measurements during the whole orbit, or if you wanted several orbits around the Earth. So the orbit was about 100 minutes. So it's like a radiometer that we can use a constant frequency. But then we can also use a radio spectrometer, so we can change the frequency. And at the beginning, because we never know how long our platform and instruments will work, so we want to collect as much data as possible. So just use those instruments and get the data. But of course, we would like to get as much useful data as possible. So then it's more complicated, because then we have to little bit also decide how to use the instrument. The local, global, which frequencies, maybe how to sweep radio wave instruments. And that's a slow process. Then we also have a every now and then joint campaigns. And especially interesting is the joint campaigns when we use ice cut radars, that they send radio waves, and we try to listen or record those radio signals when we are near those ice cut radars. I will come back to that one. So actually, to make a joint measurements, to joint our in-space measurements and on ground-based measurements, and actually active measurements. So first about the camera. And the camera is a typical white light camera. It's a wide angle camera. So because we wanted to especially take picture of auroras, so therefore we really need a wide angle so that we can capture hopefully large part of the auroras. It's a 3 megapixel camera. Of course, because it's a wide angle, the resolution is not very good. The ground resolution, but actually our goal was to really take a picture of photos of auroras. So this was the reason why we chose this kind of commercial camera product. And maybe a couple of examples about our camera. So actually what you now will see here, they are actually quite a low resolution. They are JPEG photographs, not raw data. But anyway, we are happy about the quality of those pictures. And maybe we gave a little bit, I'm using names for those photographs. For example, here we give the name for this photograph, Hope Overcomes Despair. And what the reason why we gave this name is that on your right-hand side, you can see a little bit dark colors. And actually, it a little bit also a little bit shows that everybody who have been in space projects knows that there is times that there are some very bad problems. And it might be that you are a little bit despair what will be happen at all. But then in our project, we also had difficult times, but finally we came from, in this photograph, to the left. So you can see bright light. So actually we have to knock the wood that finally we successfully went to space, and we have got nice amount of data. But you have to really be prepared that things doesn't automatically go well. So hard times, but in the best case, you can also get some reward and get the fruits. In the previous picture, it was one photograph, but here actually you can see connection of or panorama of 2 photographs. The name is the Outer Hebrides, so it's a part in the northern of Scotland. And actually, I wanted to show is that because one problem in small satellites is that is the attitude control. It's very difficult to really control the attitude, but always, practically always, is making some kind of rotation, uncontrolled rotation. But you can also use this feature. You can benefit that feature. For example, here we took photographs in a certain frequency, and when the spacecraft was rotating, actually we could combine 2 photographs taking a little bit to different directions. And here, for example, you can connection of 2 photographs taking when the spacecraft was rotating. We cannot change the attitude, the direction of the camera, but the spacecraft is changing, so that this makes that possible. And actually, this is the panorama taking from 3 photographs. And if you look the first slide, the introduction slide, actually you show a part of this photograph or this panorama. And actually, our colleagues from Finnish Meteorological Institute say that it's a jet stream, what you can see here. It's associated. And here you can see actually a panorama made of 5 photographs. We call it like towards light. And actually here you can see the whole field of view, what we can see on the left in this kind of narrow field of view. And you can see the little bit like a ground sea and clouds from the bright to the dark side. But now this was example about our day side. So already those those examples made it clear that our camera looks to work. It is in the focus, colors look to be quite correct. And maybe I already now mentioned that I will come back to the importance of calibration. So before we launched before the launch, we calibrated our camera in our laboratory by using monochromators. So we really devices that send a specific, very narrow wavelength range. So we make a calibration by using those frequent wavelengths what are important in auroras. So red color 630 nanometer and the green color 557.7 nanometers. So we really use those wavelengths, and we take photographs in our laboratory so that we really see what is our camera response to those aurora images. And here actually you can see our photograph of aurora. So the aurora is actually a little bit background. You can see a vertical extension of red and green colors. But actually we have also marked by hand a name of stars behind the aurora and also constellation. And actually that's the reason why we call it like a Aquila auroras, because you can see the constellation below. And maybe already know one thing. So we don't have a GPS in our satellite. And actually we don't exactly know, we don't know the altitude. But that actually when we analyze the aurora images, so the nice thing is that we can use stars to really to analyze the altitude. And for example, here it was very easy to look what is the direction to where our camera is pointing when we use those stars. And we also use moon and stars for calibration purposes. So the calibration, of course, it's important. And actually, many times when you have a optical instrument in space, you have to make a constant every time, every now and then, a calibration to really make sure that your instrument sensitivity is about the same, or if it's not, typically it's sensitivity is going down, and therefore you have to a little bit use different calibration constant. For example, here, for curiosity, this was taking almost exactly 50 years after the Apollo mission took this kind of very famous Earthrise photograph. But now, because we are around the Earth, so we call it like a moonrise. Our goal was not to take good pictures about the moon, and so therefore the moon is quite a small spot. in our wide-angle camera. But anyway, it's nice that we could anyway get many pixels, and actually we are now accomplishing a paper that we actually compare our moon photograph to the simulated moon image. Then we also take a picture of stars. In the previous one you saw one spots, but we also have some kind of automatic made a recognition of stars. And this gives an example of our paper that is we are now just accomplishing, that we used photographs. Those photographs, you can see name of the stars, and there are two small photographs. What you can see on your right hand side, this little bit messy small pictures, they are taking from the photographs, and your left hand side you have see simulated from our camera model. And then when we make a camera model, we make a model of the spectra of the stars by using star occultation instrument data, and also different analytical models. And so we have made also a calibration to our instrument in space using the moon and stars. And as I mentioned, one goal is that because we have one unit, two simple instruments, but we have on ground a lot of instruments. And here you can see actually the map, and map at the center there is okay, there you can see the Finland, you can see you can see Greenland, East Iceland. Those couple of curves, green and red curves, actually they are approximately the region where we took this where we took, maybe this mouse is working, yes, this region is the region where we took, where the auroras are located. But in addition to our photograph, we also have many all-sky cameras. For example, here we have a Kilpisjärvi, here we have a Kevo, all-sky cameras, field of view. Then we have also this kind of Långerbuen and very wide field of view. And then there is also scanning photometer that to take data from this region. And then we, of course, we have really many magnetometers. So this means that we are actually now combining our photograph to other photographs taking at the same time from the same region, and also the magnetometer data of what we have. And I think that the one power of to optimize small satellite data is that you can really combine that data to the ground-based observations to really combine, so to say, space infrastructure. Okay, one CubeSat is not the infrastructure, but anyway, data from to space to really to ground space infrastructures. Then the radio wave spectrometer, another instrument. So as I mentioned, there is this kind of 3D printed peak, and there you can see antennas. Then you can see PCB board, and it is designed, built at Aalto University. Maybe already now I didn't maybe mention, but so the philosophy of this our Suomi setup was different than our Aalto University Space 1, Aalto 1 and Aalto 2. Because now we really wanted to focus on space instrumentation. So actually this radio wave instrument is the first CubeSat instrument what we have developed and built at Aalto University. So we didn't build the platform as we did in Aalto 1 and Aalto 2. It was the commercial platform. so that we can really focus on to build an instrument, as reliable instrument as possible. And this it was our main instrument. As maybe I just mentioned, it is from optimized from few megahertz to about 10 megahertz, so mainly to HF ranged, and then, as I mentioned, commercial components. What kind of signals? So there are this kind of natural signals. One is, for example, this kind of type 3 solar storms when high energy electrons forms, radio waves. For example, here you can see data from Cassini from different wave frequencies, and actually this is the frequency range, for example, when where Suomi is. So at least we could, if there is a type 3 storm, it really would produce signals that we could observe that is in our frequency range. Then there is also all kind of noise. So man-made radio signals that is not made purpose for research purposes. For example, here you can see a signal that might be come from different places, let's say from India, from California, Australia. Here you can see, actually now the distance is very far. We are 32 Earth radius. But if you have a sensitive instrument here, you can see that some of those radio waves can really go through the ionosphere. And also in our frequency range and in other frequency ranges. So there is always a radio noise in those frequency range that we are measuring. But actually what we are interested is that to really make a joint measurements, to really make active measurements. As I mentioned, we have many instruments in Finland and in Scandinavia. And I already mentioned IceCat. So we have radars. We are now building in Scandinavia IceCat 3D, more sophisticated radars. And as I mentioned, we have all sky cameras, we have magnetometers and ionosomes. And especially interesting is that those radars, because in radars, in this plot, this is the altitude up to 600 kilometers. Our Suomi altitude is about 600 kilometers. So here you can see the distance. Actually, this is the diameter approximately to Finland. So this gives a schematic illustration that when you send radio waves in a few megahertz range, part of those radio signals, let's say over 10 kilohertz, they can go through the ionosphere, and we can really then listen those and maybe observe those radio waves. But as you can see, this sketch, radio waves are not propagating directly because there are ionosphere charged particles that are affecting to the propagation of electromagnetic waves. And it also means that when we know when we hear, in which frequency we hear radio waves, it gives information about properties of the ionosphere, electron densities. So, and this is this kind of active measurements what we made in IceCat. IceCat sent radio waves, and then we try to listen those radio waves. So we call it like actually they are HF transmitters or heaters in Tromsø, in Norway. And actually there are 3 antennas. They are actually different frequencies from 4 to 8 megahertz in several megawatt pulses, or the energy, corresponding energy. And maybe one limitation, as I mentioned, I will actually mention later also that when you build a simple instrument, then you have to pay that for some reason. And you have to pay it typically that it takes a lot of time to make a data analysis. The amount of information is limited, and you have to then try to make different models to really understand that data. For example, we have such a simple omnidirectional receivers, antennas, that we don't know from where the signal is coming from. And therefore, we have developed different tools to investigate from where that signals can come from. And for example, here we put a spacecraft here, and then we look by using so-called ray tracing program. In ray tracing, we follow how the radio waves are propagating. As you can see here in this frequency range, radio waves are not propagating like a straight line because of the ionosphere. There are part of those signals what we can get, they may come from the ground. Part of those could come here, they are red signals. Part of those actually can then come from the space. So that those blue rays. And so it means that we have to use this kind of model, try to understand what is the source of the signal. And here we can, this gives another data analysis tool. So when we make this kind of ray tracing proposal here, you can see rays transmitted and 7 megahertz from Helsinki. Then our satellite is flying, let's say, about 600 kilometers altitude. So we are interested about what kind of radio signals we can get at this altitude on this plane. And so we have make simulations that if you investigate the signal of the strength, if you have 1 point signal here, you can here see that what is the strength of the signal around this point source. And this also helps us to understand what might be the source of the signal on ground or from space. And actually here you can see, as I mentioned, when we use the radio wave instrument, we can make this kind of, we can collect data 1,000 data points per second at maximum. And we are using that kind of data mode when we make ice cut heater joint measurements, because we get so much data. Actually, I forgot to mention that the last time when we make that ice cut heater observations was at the beginning of December, so 3 months ago. And we are now downloading the data from that measurements. Actually, it's we have such a low data, telemetry data. We have now. It will take still several months before we have get down the data that is kind of ice cut heater data down. But here we see a little bit older data from 2019, and here we used this kind of low telemetry data. Low data rate observation mode. So only 5 data points per second. And as I mentioned, then we can collect the whole orbit or several orbits. And here we use a radiometer. So you use the same frequency during the whole orbit, about 8 megahertz frequency. And you can see when you look the data, actually you can see the color means that the red means that there is a low signal strength. Red and especially yellow and white means that there is a high signal. So you can see all kind of small scale rapid variation in the data for many reasons. For many reasons. There, of course, there is many radio wave sources here, and actually it takes a lot of time and we are still working it, try to really separate what is the, let's say, some man-made noise and what is the real signal, let's say, from space. But in addition to this kind of small scale rapid variation, you can also see certain trends, global variation. And for example, here we can see that when you are in the region, in a region on the day side, when there's a strong ionosphere, the signal is low. And actually, this is something what we expected to see if we have a, let's say, homogeneous radio signals emission or noise around the Earth. So then the ionosphere blocks effectively, especially in those regions when the spacecraft is above the day side and the strong ionosphere. So this is actually the trend what we a little bit expected to see on the theoretical point of view. But this was where I would like to end now, and maybe some concluding remarks or the lessons. So some lessons is that try to reserve as much time for testing as possible. So testing of the platform, of course. If platform doesn't work, of course, it doesn't help if your instruments are working. So test the platform, test and try to avoid very hard deadlines. Our case is not good example in that respect, because as I mentioned, our satellite was a cubesat satellite, and actually we got a pressure from the around Finland and also from the government that we would like to have the satellite in space at the time when we celebrated this 100-year independence. But unfortunately, we didn't made it because of launch delays. Actually, our first launch region was to launch in India. But in India, they have problems with their launcher, actually the last state, and that did cause delays. And actually, this is because of those delays, we finally decided to go to California, because it looked to be that we can go to space earlier than to wait launch from India. But actually, we went to space almost 1 year later than planned. But unfortunately, we had to prepare to deliver our spacecraft at any time. So it also means that we have our platform and spacecraft in Finland, but we couldn't make a testing because we have to be prepared to deliver it immediately and to really celebrate this jubilee event. So that was bad to us, because if we would have known that our launch is only about 1 year later than planned, we would have made more testing of the platform and more testing of the instrument. As I mentioned, we made some simple tests for the camera instrument, but only 2 frequencies, 2 wavelengths, and actually very simple, quick testing. But now when we analyze the data, we recognize that it would have been good to make a more comprehensive testing for color. And actually, this is one reason why we make now testing or calibration in space by using the moon and the stars. Of course, this is nice that we have this kind of calibration facility, natural calibration facilities in space. But we have more difficult problems to interpret our radio wave instruments, because we have had possibility to make detailed radio wave radio instrument calibration only by using our second radio instrument, our flight model spare instrument in laboratory, but we never had time to really make to calibrate our space spectrometer that is in space, and this really certainly complicates data analysis. And then, as I mentioned, please prepare of all kind of delays, components. If you buy subsystems, you have to have all kind of licenses to get your hardware into space, facilities to test or to build, and as I mentioned, to launch delays. And all kind of problems, typical problems, time schedule, funding problems, maybe manpower, and especially if you have a students are only part-time in the project. Of course, they have to make their thesis and accomplish their studies. So it also makes sometimes a lot of difficulties in the project-wise, as I mentioned, components and many other things. And then, as I mentioned, data analysis can be very slowly because your instruments can be very simple. It might be that you haven't calibrated those enough, so you have to really make calibration in space and put a lot of efforts to make, let's say, simulations and other data analysis tools. But I'm sure that all the members in our Suomi satellite project share my feeling that it's really worthwhile to go that trip. It was really worthwhile to do that. So thank you for your attention.
Yeah, Esa, thank you so much for this very detailed report and presentation. I'm happy that your 1 year, right? 1 year project end up so successfully.
If you have questions, please, I'm happy to answer.
Okay, yeah. Let me see who else had the. Yeah, I'm asking that are you using only one single receiving station?
Yes, I forgot. Maybe I a little bit changed the scene. Yes, we have a ground station at Aalto University, so it's at the top floor. Dr. Antti Kestelä will give the presentation, and actually he will show a couple of photographs taken from our ground station. And then, as I mentioned about the licenses, we are allowed to take the signal down only by using this one ground station.
Any questions from the audience? Please, unmute yourself and ask the question.
Esa, I wonder why specifically are you only allowed to downlink your data through that one ground station? Usually for cubesats and most small satellites as well, there shouldn't be an issue with using ground station networks, or in your case, getting data downlinked through either another university or one of those nice CubeSat compatible ground station or ground relay network providers. Is there some legal issue for you guys, or what is the problem?
Yeah, yes, it is, because so we had to ask to use permission to use this frequency range. So it's not allowed to just put a transmitter to transmit this those signals. So first we ask that from the it might be that Antti Kestelä can answer more those technical things, but we first asked from this kind of universal, how to say, this kind of institute, and then we have to also ask that to use this frequency from our government. So then, as I mentioned, please prepare to spend time of licenses. So we really had to make a request that we use this frequency, and then we have to give information about what is the power of our transmitter, and then finally we get a permission to use this signal. But then actually we got several complaints from around the different places around the Earth that somebody said that they are using this frequency range for different purposes, or it's close to what they are using. Some country, for example, is using their purposes, and then we have to describe describe that we don't cause harm because our signal strength is so weak. So it wasn't. It was quite a long process. Actually, it took over 1 year that we get a permission to really use that signal. But it is true that nowadays there are companies and you can buy. You don't have to get your own ground station. You can buy services that some ground stations, maybe several ground stations around the Earth, takes down the signal. But we really made it by ourselves for educational purposes.
Other questions? If you have other questions, please, unmute yourself and ask the question. Esa, I want to know, is the Suomi 100 still working, right? It's still running.
Yes, I knocked the wood that it's working. And as I mentioned the last time, when we make this kind of very intensive testing, was that we use our radio spectrometer on December. And at the moment, we are every day getting down part of that data. So it also tells that because we are getting down the data, the spacecraft is working. We can send the commands and we get the data. And after maybe 2 months from now, when we have get down the data, so we can then continue to use the radio wave instrument. And hopefully we can also sometimes start to reuse our camera instrument. But in my mind, the radio wave instrument is the most useful. And we have made calculations that it might be that the spacecraft is in space almost 20 years, a little bit less than the 20 years. Of course, it depends on the activity of the sun. But unfortunately, I'm sure that we will not get data from such a long time. But I would say every day when we get more data, I'm happy. And actually, this was the reason why we started to get as quickly as much data as possible, especially as everybody knows that if you have a satellite camera and photographs, they are very important for outreach purposes, for example. And this is the reason why we want to take a lot of photographs for this kind of outreach purposes. But now at the moment, we move focus to this kind of detailed science specific questions.
It would be wonderful if you could take a picture of Taiwan and send it to us.
Yeah, I will keep this your interest in my mind when we start to use the camera. Thank you.
Okay, that would be great. The Finland-Taiwan cooperation.
I agree. I agree.
Okay. Any other questions? If not, I will let Esa go. Have a rest, and then we still have about 5 minutes, and then we could go out and take a coffee, and come back in 5 minutes, and for the last talk of the session. Thank you, Esa. Great talk.
Thank you very much.
I will write to you again. Yeah. Thank you.
Thank you. Bye bye.
Bye bye.